IF Wainfleet Range, Lincolnshire, July 1942. A line of black mosquitoes sits under the thin haze of an English summer morning. Their engines are silent, but the smell of fuel and salt air drifts from the North Sea. Crews move quietly between the aircraft, chalking notes on aluminum panels and marking dive angles in white paint on the tarmac. The air is dry, the wind steady at 12 knots. Over the control hut, a signal flag hangs limp, waiting for the first sortie. Inside the operations hut, squadron leader Benny Goodman studies a hand-drawn map. The paper has been folded and refolded until the creases have gone white. Circles mark the bombing range, the estuary mouth, and a series of approach paths mark dive, 60 degrees, entry 4,000 feet. His pencil traces the line downward, stopping at a notation, impact, plus 5 seconds delay fuse. The test is unauthorized in every sense but one. The orders came from an engineer at Farnborough, not from Bomber Command. Goodman's task is to find out if a controlled dive at extreme speed can plant a bomb close enough to a small bridge target to matter. At 9:10 hours, the first Mosquito taxis to the edge of the range. Observers record the details on clipboards: aircraft DZ-647, Merlin 21 engines, 500 pounds GP bomb, Type 28 release gear. The range officer calls the wind, then lowers the flag. The aircraft accelerates, the twin propellers blurring to silver discs. Goodman holds the nose level until the coastline disappears beneath him, then pulls back sharply. The Mosquito climbs to 4,000 feet and rolls inverted. At the apex, he pushes the stick forward. From the ground, the dive looks suicidal. The silver aircraft falls like a thrown knife, the angle impossible to judge by eye. The observers hear the pitch of the engines rise beyond safety limits. At 1,200 feet, the wings flicker, then the bomb falls clear, tumbling for precisely 5 seconds before the impact flash. A white column of smoke rises from the target raft. The observers note, direct hit, lateral error less than 20 feet. Goodman pulls out at treetop height, the Mosquito skimming over the marsh. The altimeter needle oscillates wildly. He radios a single word, confirmed. The aircraft banks low and vanishes behind a ridge. On the ground, engineers mark the crater with red flags and measure the distance from the raft center. They photograph the strike using a Greyflex camera, then recover the casing fragments. The data will be used to recalibrate the RAF's low-altitude bombsight, Type F. The test continues throughout the day. Each run increases the dive angle, 60, then 70, then 75 degrees. At 80 degrees, the Mosquito is descending almost vertically, reaching terminal velocity before Goodman pulls out with less than 200 feet of clearance. The aircraft's undercarriage doors flex under the pressure. Mechanics find hairline cracks along the fuselage after each sortie, recorded in the maintenance log as structural fatigue at frame 28. According to range records preserved in the Bomber Command experimental reports, 1942-43, these tests were never meant to become standard. They were designed to find the practical limits of pilot endurance and airframe stability. Yet in less than a month, the method had produced results no level bombing run could match. Goodman's name appeared only in the technical annex, a single line: Flight Officer B. Goodman, test pilot, conducted steep-angle precision trials under Wainfleet control. By sunset, the coastal light turns gold over the empty range. The sea reflects the glow of the last impact plume. Technicians lock away their logbooks, and the pilots walk back across the grass, silent except for the distant echo of the final detonation. The day's results are tabulated and sent by courier to Farnborough. The data sheet reads simply: average miss distance, 14 feet. Dive speed, 360 miles per hour. Altitude at release, 1,100 feet. No announcement follows. The experiment remains unclassified but unnoticed. In the next month, those numbers will begin to shape a new doctrine, one that will turn suicidal dives into the most accurate bombing tactic the RAF ever developed. By 1942, the technical staff at Farnborough had built a small laboratory of the sky. Engineers sketched trajectories on damp graph paper under a bank of lamps. They marked airspeed against terminal velocity, then overlaid blast radius curves from WWI-era ordnance tables. Each plotted line represented a trial flown earlier that morning at Wainfleet. The data were raw, altimeter blips, stopwatch readings, and stamped film from underwing cameras, but patterns began to emerge. Goodman's technique introduced two variables unfamiliar to bomber command doctrine: extreme dive angle and near-surface release. The dive reduced horizontal drift caused by wind shear. The near-surface pullout shortened the bomb's exposure to crosswinds. Engineers confirmed this empirically by comparing paired runs flown at identical headings. In each pair, the steep dive run showed a lateral error reduced by a consistent factor. The math was straightforward: release later, reduce time aloft, reduce drift. Instrumentation required modification. The low-altitude bombsight, Type F, had been calibrated for level runs at 2,000 feet. It could not compute release timing for a 70-degree descent. Farnborough technicians fitted a temporary analog compensator, a rotating cam linked to the sight's index, which adjusted for changing vertical velocity. The compensator used a lookup curve derived from terminal velocity tests of the 500-pound general-purpose bomb. The curve was punched into a metal disc and secured behind the sight's glass. Pilots learned to read a single green mark as the aircraft passed a pre-calculated angle. Flight procedure standardized quickly. Approach began at 4,000 feet on a fixed heading. At the dive point, the pilot rolled smoothly, pushed the nose down, then kept throttle at a calibrated setting. The aim was not to fall uncontrollably but to establish a steady vertical component of velocity. Release timing was based on three cues: altimeter, angle of attack indicator, and the sight's compensator mark. The pilot spoke one word to confirm: set. Ground observers recorded the release sequence to the nearest tenth of a second. Technical notes describe the physiological effects on pilots. High G loads at pullout tested human limits. Pilots reported tunnel vision and metallic taste during sustained 75-degree dives. Recovery techniques were developed: slow, staggered pullouts, fixed duration breath holds before maneuvering, and a routine medical screening focused on blood pressure stability. Flight surgeons logged the findings in terse language. Transient visual impairment noted under +4.5 G. Recommend 12-hour rest post-trial. Aircraft limits were equally exacting. The Mosquito's plywood structure flexed under sudden load changes. Engineers adjusted maintenance intervals, replacing stressed bolts at frame 28 more frequently. They added reinforcement plates where hairline cracks developed. Ground crews annotated every change in the service log. Each modification entered the experimental ledger with a reference code, FARN 42's MOSREV3. Range measurement improved too. Ground teams moved from visual estimates to photographic triangulation. Two Greyflex cameras, set 20 meters apart and synchronized by chronograph, captured the moment of detonation. Analysts converted the film frames into coordinates using scale bars placed beside targets. That change reduced measurement error by half. The resulting data substantiated the claim Bomber Command would later accept: steep angle releases produced repeatable, precision strikes within yards rather than hundreds of feet. Operational application followed rapidly. Small-scale raids testing the method against hardened points of interest confirmed the laboratory results. Target selection favored structures where proximity mattered: bridges, small workshops, and guarded compounds. doctrine papers began to recommend a new class of operation, low-level precision raids, LLPR. The concept traveled fast through memos and shorthand notes. By autumn the term appeared in a technical appendix distributed to squadron commanders. According to Farnborough correspondence preserved with Bomber Command files, the shift was pragmatic, not doctrinal. The memorandum advised limited adoption and emphasized risk mitigation. Yet the recorded strike accuracies could not be ignored. Engineers and pilots had converted an experimental dive into a predictable instrumented technique. The observation sequence closed the gap between intuition and repeatability. Following these trials, analysts compiled a comparative dossier of standard level bombing versus steep dive precision runs. The dossier contained the numbers that would change planning rooms across the RAF, average miss distance, standard deviation, release conditions, and recommended fuse delays. Those figures will form the basis of the next segment, an examination of how measured results became operational doctrine. Farnborough analysts presented their first consolidated report in September 1942. The cover sheet listed test conditions, aircraft types, and wind readings for each sortie. Tables followed: release altitude, dive angle, terminal velocity, and lateral error. The raw numbers were terse, precise, and immediately persuasive. Across 42 instrumented runs the mean lateral error measured 14 feet. The standard deviation of those runs was under 10 feet. By contrast, matched level bombing trials averaged miss distances exceeding 180 feet. Those figures appear repeatedly in the experimental ledger under index FARN 42 EXP. Engineers converted photographic triangulation into simple curves for operational use. A plotted line showed lateral error falling sharply as dive angle increased. Terminal velocity explained most of the improvement in wind drift reduction. Shorter time aloft meant less crosswind influence on the bomb's trajectory. Farnborough staff quantified the relationship with a release time equation. The equation linked vertical velocity and exposure time to expected drift. Using that formula, planners could predict miss distances within a narrow band. Accuracy thus moved from anecdote to calculation and intermission planning. Bomb fusing required concurrent revision. Delayed action fuses had to account for the bomb's different approach vector. A 5-second delay, standard in tests, prevented premature surface bursts. Analysts recommended fuse timing windows for common target profiles. Those windows were written into the Type F site appendices. Damage assessment teams correlated crater geometry with calculated impact angles. Explosive engineers confirmed penetration profiles matched predictions. That confirmation elevated the technique from precision to tactical effectiveness. Bridge abutments, small munition stores, and lock gates were most vulnerable. Operational reports later cited multiple successful attacks against these target types. Human factors entered the dossier with equal clarity. Medical officers recorded pilot tolerance thresholds for sustained high G pullouts. A table listed recovery times, visual impairment incidents, and recommended rest periods. Pilots with prior aerobatic training performed better under repeated stress. The Farnborough memo recommended selection criteria for LLPR crews. Training syllabi were drafted to include simulated pullout sequences. Mock-ups of the compensator disc were used in cockpit drills. Ground crews rehearsed rapid airframe inspections after high-stress sorties. Maintenance cycles were shortened and detailed in a new technical order. Risk assessment balanced accuracy gains against loss rates. Aircraft attrition during LLPR trials exceeded doctrinal averages in initial weeks. However, the improved accuracy reduced the need for repeat raids and massed formations. Fewer aircraft over a target often meant fewer exposure hours to enemy defenses. Planners ran comparative models weighing single-run success probability against formation losses. Those models showed net mission risk decreasing for small, high-value targets. Farnborough forwarded the dossier to Bomber Command with a cautious cover note. The note emphasized experimental status and urged pilot selection care. Bomber Command convened a technical review board in October 1942. Board minutes show brisk debate between operations officers and engineers. Operations favored gradual adoption in theaters with suitable targets and cover. Engineers insisted on maintenance standards and crew medical screening. The board approved limited operational trials under controlled conditions. Within 2 months, modified Mosquito crews trained on night intruder and coastal raids. Their first operational successes mirrored Farnborough's predictions precisely. After-action reports recorded average miss distances consistent with laboratory data. Photographs of damaged targets corroborated predicted blast and penetration profiles. The empirical match turned an experimental technique into a doctrinal option. The realization was technical and narrow, steep-angle low-level release produced superior precision. That single, measurable fact changed mission planning for select high-value targets. By early 1943, the steep dive method had moved beyond trials into selective practice. Squadron logs show discrete taskings, sabotage of rail bridges, precision attacks on coastal pumping stations, and strikes against small, dispersed supply depots. Mission orders specified approach corridors and release parameters drawn directly from Farnborough tables. Commanders annotated maps with recommended fuse delays and pull-out profiles. The language in orders was technical and spare: approach 040 degree, roll at 4,000 feet, release at 1,100 feet, compensator mark, green. Tactical planning adapted to the method's strengths and limits. Planners chose targets where hit proximity mattered more than blast mass. Small bridges and signaling installations became priority targets because a single well-placed bomb could render them useless. Intelligence officers altered photo reconnaissance priorities to include structural vulnerability assessments. Engineering sections produced short briefs showing how a 90-degree shear against a bridge pier produced different failure modes than a shallow-angle strike. Those briefs appeared in mission packets distributed to crews days before operations. The method also influenced crew composition and training. Bomber Command developed an LLPR cadre program emphasizing gunnery discipline, navigator precision, and physical resilience. Pilots underwent simulated pullouts in link trainers adapted with modified site mock-ups. Navigators learned to calculate final heading corrections for crosswinds at low altitude. Air gunners practiced immediate suppressive fire drills to protect aircraft during pullout recovery. Medical screens became part of crew selection, cardiology checks and visual endurance tests were recorded in service files. Those criteria are visible in surviving personnel records. Material changes followed. Workshops installed reinforced fittings at frames identified by Farnborough engineers. Sighting compensators were manufactured and issued as squadron kits. Maintenance orders mandated inspections after any operation involving angles over 70 degrees. The Mosquito's plywood skin received localized reinforcement at stress points. Ground crews kept stamped logs of bolt torque and plate replacement dates. The procedural rigor of these mechanical changes reduced attrition previously observed during early trials. Operational doctrine incorporated LLPR into combined arms planning. Army staffs began to request LLPR support for raids intended to isolate enemy rear areas. Naval intelligence used LLPR to deny small coastal installations used by E-boats. The technique did not replace strategic area bombing. Instead, it became a surgical option within a broader campaign toolbox. Doctrine papers of 1943 and 1944 reflect this. LLPR appears as a recommended tactic for high-value, limited objective missions. The method's limitations were documented candidly. Adverse weather reduced the method's reliability. Heavy cloud cover obscured visual markers needed for final release. Enemy flak at low altitude caused disproportionate risk. The flying stress on airframes required close monitoring. Commanders balanced those costs when assigning missions. Statistical annexes retained with Bomber Command show mission success rates alongside loss rates, enabling a measured view of trade-offs. Post-war assessments treated the Farnborough tests as a case study in rapid applied engineering. Analysts noted how a single empirical experiment, executed carefully and measured precisely, translated into an operational capability. The reports praised the systematic documentation, flight logs, photographic triangulation, compensator calibration records, and medical screening forms. Those documents allowed planners to replicate the technique across theaters and aircraft types when conditions permitted. Culturally, the technique left quieter traces. It altered training syllabi, maintenance calendars, and target selection logic. It changed which targets were considered feasible objectives and which remained impractical. The method also reshaped the relationship between engineering staffs and operations officers. A procedural channel formed connecting laboratory analysis at Farnborough directly to squadron briefings. That channel persisted beyond the war, informing later peacetime development of tactical bombing doctrine. Technically precise and operationally narrow, the steep dive method did not revolutionize air war strategy. It did, however, provide a predictable solution for a specific problem: how to deliver a single bomb with minimal lateral error against a compact, high-value target. That pragmatic contribution altered mission planning, reduced the need for repeat attacks, and preserved resources across multiple campaigns. One calm realization closed the file: measured risk plus precise data produced a reliably accurate weapon system. Squadrons moving from experiment to execution followed a strict syllabus. Training flights reproduced Farnborough timing with progressively increased realism. Pilots practiced under simulated stress in link trainers and limited dual sorties. Navigators ran wind correction tables at low altitude until calculations became second nature. Ground crews rehearsed rapid inspections and bolt torque checks between sorties. Maintenance orders specified reinforced fittings at frames indicated in experimental logs. The method found early operational use in coastal interdiction missions. Small coastal depots and signaling posts proved ideal for single bomb disruption. Intelligence officers prioritized targets where proximity of strike decided operational effect. Planners scheduled LLPR missions when recon showed discrete, vulnerable structures. Photographic intelligence included scale bars to enable exact compensator settings. One recorded operation illustrates the method's procedural rigor. A raid tasked a Mosquito flight to sever a rail spur feeding a coastal depot. Briefing packets contained approach headings, compensator marks, and fuse delay settings. Pilots synchronized release timing with radio-synchronized chronographs on the ground. Observers triangulated the detonation using synchronized Greyflex frames for post-strike measurement. The resulting strike disabled the spur with a lateral error under 20 feet. After-action notes emphasized adherence to compensator settings and precise pull-out timing. LLPR also supported commando-style operations requiring surgical destruction. Small bridges and lock gates were high-value priorities for local commanders. A single properly placed bomb could deny transit for days or weeks. Army staffs included LLPR options in combined arms planning for re-area interdiction. Naval intelligence requested LLPR strikes to neutralize coastal launch ramps for fast craft. Adaptation to aircraft other than the Mosquito followed documented engineering practices. Each airframe required unique compensator curves derived from terminal velocity tests. Lancasters and Beaufighters received procedural appendices noting structural limits. Engineers specified reinforced fittings and revised maintenance intervals for each type. Operational orders limited angles and pull-out speeds per aircraft service bulletin. Loss rate data governed doctrinal adoption across theaters. Early attrition during trials gradually decreased as procedures and maintenance improved. Command risk models compared single-run success probability against traditional formation losses. For particular target profiles, LLPR reduced overall mission exposure and enemy engagement. Those models shaped the RAF's selective use of the technique in 1943 and 1944. Field reports provide unvarnished assessments of human cost and tactical value. Pilots describe brief visual impairment during recovery maneuvers in terse log entries. Medical files list short-term visual disturbances and recommended rest protocols. Training screens and selection criteria reduced incidents among repeat crews. The procedural discipline around crew selection became a routine part of squadron life. The technique's reproducibility made it attractive for targeted sabotage operations. Fewer airframes were required to achieve an intended tactical effect. That economy mattered where resources or cover were limited. The LLPR option offered commanders a controlled risk with predictable outcomes. Post-war technical reviews recorded LLPR as an example of rapid field engineering. Analysts credited careful measurement, photographic triangulation, and compensator calibration. The method illustrated how empirical tests could convert an unsafe maneuver into doctrine. Farnborough's ledgers, bomber command memos, and squadron after-action reports preserve that trail. Those documents show a chain running from single experiment through standardized operational use. The lesson contained in the files is procedural rather than heroic. Precise measurement, iterative modification, and strict procedural discipline made accuracy routine. A pilot's suicidal dive became, through engineering and documentation, an instrument of control. That control allowed planners to design missions around effect, not mere area saturation. In doing so, the method quietly altered tactical choices across multiple campaigns. By mid-1944, the steep dive procedure was an established option in planning rooms. Operational orders listed LLPR as a recommended technique for discrete, high-value objectives. Mission packets reproduced Farnborough tables alongside target photographs and compensator settings. Commanders used the technique selectively where a single bomb could produce strategic delay. Records show LLPR reduced the need for multiple sorties against the same target. Intelligence staff correlated fewer repeat attacks with decreased enemy repair rates. A single precise strike often denied vital infrastructure for days, sometimes weeks. That immediate effect translated into diversion of enemy resources away from frontline operations. Technical records continued to evolve after first adoption. Engineers refined compensator disks for additional bomb types and fuse combinations. Maintenance instructions standardized reinforcement plates and inspection cycles across squadrons. Flight surgeons extended medical screening protocols to cover cumulative G exposure. The method spread remained measured and conditional. Weather limitations, low-altitude flak, and tactical context shaped each authorization. Planners assigned LLPR only when reconnaissance confirmed visual release markers. Where clouds obscured the sight line, planners reverted to proven level bombing doctrine. Case files illustrate the method's mixed legacy in human terms. Some crews recorded mission success with minimal aircraft damage. Others logged severe airframe stress and near-loss incidents during aggressive pullouts. Service records show promotion boards weighed operational effectiveness against crew attrition. Post-war technical analysis settled on a pragmatic judgment. Steep-angle low-altitude release was neither universal solution nor reckless novelty. It was a tool that solved a narrow class of tactical problems with predictable results. That assessment appears in Royal Air Force doctrinal reviews through the late 1940s. Historians later credited Farnborough's empirical discipline for the method's success. Photographic triangulation, synchronized chronography, and maintenance logging provided replicable data. Those practices converted an improvised experiment into reliable operational procedure. The procedural chain ran from bench calculations to flight trials and into squadron orders. Institutional relationships changed as a result. Operations officers began to consult engineering staffs earlier in mission planning cycles. Laboratory findings reached line squadrons faster through formalized technical appendices. That organizational shift persisted beyond wartime urgency into peacetime tactical development. The steep dive method also influenced Allied thinking on precision delivery. Its emphasis on measurement, instrumentation, and crew selection anticipated later guided munition approaches. While technology would eventually supplant manual compensators, the conceptual link endured. Precision, rather than volume, became an increasingly valued principle in tactical doctrine. Archival documents preserve the method's quiet footprint. Bomber command files, Farnborough ledgers, and squadron after-action reports record the full chain. Photographs of impact craters and compensation discs remain in technical annexes. Medical logs and maintenance orders complete the operational picture with human and mechanical detail. One final operational truth emerges from that documentation. Accuracy comes from disciplined testing, not from daring improvisation alone. Goodman's dives provided raw possibility, Farnborough's measurements made that possibility predictable. Measured risk plus precise data produced a reliably accurate weapon system. The war did not hinge on a single pilot's courage or a single risky maneuver. It hinged instead on the steady work of technicians, engineers, pilots, and clerks. Each entry in the ledger, each stamped photograph, and each signed maintenance order mattered. Together they turned a suicidal dive into a repeatable technique for surgical effect.